Right, so good morning everybody. Yeah, so I always kick off at 3 minutes past just because stragglers cause so much disruption. It's just better waiting that 3 minutes and having a better lecture. Guys? Thanks. So I wanted to ask you about the coursework today. So this is like a class participation activity, and it's very important you participate. Who's finished the coursework? Hands up. Okay. Who's done? Hands up if you've done question 1. 2, 3, 4, 5, 6, 7. Are there? How many questions are there? 7. So now I said to you at the beginning of this course, I don't want this course to be stressful or for you to be stressed out. So I've got some questions. Who would like me to distribute coursework to already? Okay, I'll do that for those people that are ahead. Now, who would like more time with coursework 1? Hands up. Who wouldn't like more time? Okay, well, I'll tell you what I'll do. I will, because there's some people in the class that are going very, very fast and have done it before, and there's some people in the class. Guys, I can't talk over you. Thank you. So there's some people in the class that are going very, very fast and find it very easy, and there's some people who are sort of, brand new, a bit difficult. So what I'm going to do is I'm going to give everybody another week to hand in coursework 1, if they want to. So that makes it all much more relaxed, and you've got like another examples class, and for to get extra help. So you've now got 2 examples classes to get more help with the coursework. And for those people who are going really fast and want more work, I'll distribute coursework 2 today on Moodle, okay? And I'll hand out a paper copy next week. So that should sort of help people, who are fast or slow. Happy with that? Yeah? Okay, good. Oh. Thank you. I don't normally get that in my lectures. I normally get booing. Okay, so the other thing, so at the beginning of this class, I did mention that I want this to be like, to help you learn MATLAB. I'm not really interested in the exams and the coursework. I want you to learn MATLAB. And I also said that what I'll be doing is videoing the lectures, and you can see my video camera at the back there, and I'll try and somehow edit them and put them on the internet so it would help you with your revision and help you with your coursework. And if you miss a lecture through illness or being away or sport or something, you can catch it up later. So what I've done is I've managed to put the first 4 lectures online, so you can watch me in reverse or forwards or however you want, or double speed, and hopefully that'll help you with your revision. So, if I like this, so if you go to the internet, there's the internet, and you go YouTube, and you go to YouTube, and you type in. You've got to remember the module code. So it's MM1CPM, yeah? Hit return. You get the first 4 lectures on the internet. So, for example, you can, watch the rocket again if you want to watch the rocket. So hopefully that'll help you revise. So, so if you miss something or whatever, is that a good thing? Yeah? Okay, good. Okay, right. So I'm hoping that helps you. Now, but what I would say is, don't rely on me doing these videos. I don't promise to do them every lecture because I've already lost the audio. IS has already lost the audio for me twice and had to recover it for me for these lectures. So I can't promise to get it right, but I'll try my best. Okay, so keep coming to lectures. What I'm saying basically, and use this as like a revision tool. Right, so then, on to this lecture. Right, so this lecture is called For and While Loops. So this is where we start to learn quite a lot more about programming, and we start to learn, some really useful programming tools and tips. And this is where we really start programming. So here's an overview of this lecture. We've got recap of last lecture, and we're going to look at something called loops. We're going to look at for loops and while loops. How many people have heard of those before? Okay, so For those who have, it's a refresher, and those who haven't, we're going to cover everything in detail so you'll fully appreciate what it's all about. And then we're going to look at something called nested loops. So last week we talked about computers in general, and I said basically I wanted to give you some type of understanding of what a computer is, because you're now starting to program them, and it's very important for you to know at least something about the computer hardware. And we looked at the parts of a desktop computer, and I handed those round, and you had a little play with them, and you could see which parts did the computation, which parts did the hard disk. Guys? Thanks. And then I told you about these embedded computers. And embedded computers are effectively computers that are embedded in something to make something smart. And I said, this is the type of computer that you guys will be programming when you get into industry, because these, you can't make a mechanical product these days that doesn't have a computer in it, because it's no longer smart. So, anything you guys are going to make will have an embedded computer, so a computer embedded in it. And sort of on one end, we've got this little nano robot on the sort of the computational grunt scale. On the low end, we've got this coffee maker. And then we talked about supercomputers. And I said, basically, you will use them, be aware of them at some point in your career. We then talked about these computers on a chip. And the beauty of these computers on a chip is we have the processor, the memory, and some storage all integrated into a single chip, which means they're brilliant for embedding into really cheap products. And in fact, basically everything today that's any product will have one of these in. And the beauty of them is they're so cheap. If you go to Maplin or RS and buy one of those, they're about £1. And if you go and buy like 10,000, they start to come about 10p. So you can make your product smart for about 10p, which is a fantastic deal. We then looked at this, and the main thing about embedded systems, I said, is they've all got rubbish displays. So you don't necessarily need on aircraft a fantastic display like this. You might just need a little dot matrix, 5-inch by 5-inch display. And I said it's very important when you're writing code for embedded systems to be able to write text out, because often you can't have fancy graphical interfaces. You've got to be able to process text and send it to the screen. And we looked at this disp command, and if you type disp, open bracket, single quote, computer programming can make me rich, single quote, close brackets, it will print out text. I also taught you about this thing called strings, and the string is just basically text stored in a variable. So we've got A equals, single quote, computer programming can make me rich, single quote. So this text is now stored in this variable, and we can now just print this text. So how are we doing for time? Are we doing very well? So I then taught you about this sprintf command, and I said it's a bit of a pain to learn this sprintf command, and there's loads of options to edit or to process text with this sprintf command. But I said it's so incredibly useful, it's worth learning, because any time you process text, you can process it exactly, or form it exactly how you want it with this sprintf command. And it's also, what's also important is it's not only a MATLAB command, it's also a command in C, and I think maybe Python. There's lots of other languages that use exactly this sprintf command. So what you've learned here is like quite a fundamental, useful thing. So for example, if I wanted to say print the speed equals 500 meters per second, fuel left equals 5,000 liters, altitude equals 10,000 meters. So this is sort of information that a pilot on an aeroplane would want to have. You go A equals sprintf, speed equals %f, then sprintf looks to the end and goes, oh, there's 500 here, pop that there. Meters per second, fuel left equals %f. Oh, replace this %f with this 5,000. L equals altitude %f meters, replace this meters with 1 to the 4. So basically, we build this string, we make a new string with these characters and these numbers, and we get a nicely formatted text string. And in the lab, there's some example sheets where you get to write out some nicely formed poetry and stuff to really get you to control text output. So you should now be able to control text output to the screen. Any questions on that so far? Nope, good. Okay, the final thing we did last week was this input command, and it's literally getting input from the keyboard. So whenever you want to read a number from the keyboard, for example, to calculate how much fuel you've got left or how far your aeroplane will fly until it crashes, you just use this input command and you go answer. This is the result where the number's being stored. So this is the variable that's storing the information you're getting from the keyboard, and input tells MATLAB to go and get data from the keyboard, how much fuel is needed, and that's the question it will prompt you. So that's it. ASCII code. Last thing I taught you last week, ASCII code. and I said it's basically a very important thing to learn because it's how all computers, robots, etc. expect information to be sent to it. So if you want to power on this robot, it will not expect the text to power on, it will expect these series of numbers. And we all had to go decoding ASCII code strings for pick and mix. Right, so that was a quick recap of last lecture. Now loops. Now, I'd say now, loops are a little bit tricky. So what I'd say is concentrate quite well for the next half an hour or so, and then when you get to the lab, I go and spend 20 minutes minimum, 20 minutes to 40 minutes minimum, playing with these loops on the example sheet that's in your lecture notes. And that will just enforce, again, what I'm about to tell you, and then it'll be easy for the rest of your life. Right, so all the programs we've written until now are called linear programs. This means they run in a straight line. So if you were to write this script or this program, you could put in a comment, start of the program, x equals 1, y equals 2, x equals x times 2, z equals x plus y. And the computer, or the chip on the computer, that process we passed around last week, will execute the first line, the second line, the third line, the fourth line. In that order, it executes one line after the next line, after the next line, after the next line. And if any of you in the lab have tried, for example, executing x equals x times 2 before you've defined x, you'll get an error because it's not got there yet. It's a stupid computer. It just executes one line, next line, next line. It's just like totally linear. And this is called a linear program because it executes in a straight line. Now, here's a program. So somebody's hired you to write some code to go into this re-entry capsule. And this re-entry capsule is is being shot up into space with astronauts on it. And it's orbited the Earth a few times, and now it's time to bring the astronauts safely to land. And somebody's hired you to program a computer on that to decide when to open the parachute. Now, if you open the parachute too early, this thing's red hot because the friction in the atmosphere, the parachutes will just burn up, and the capsule will crash to Earth, and the astronauts will die. If you open it too late, well, obviously, you've hit the ground, and the astronauts die. So your job is to write some code to open the parachute at exactly the right time. Okay, so it's just like at the low enough altitude to open the parachutes, and then you get a happy landing, and everybody goes home. And you write this piece of code. And we kick off at line 1, start. Oh, by the way, this is called pseudocode. This is like a mixture between English and MATLAB, and it's used very often in computing just to sort of get an idea across. It's not actually programming. It's just sort of English that looks like programming to make you think about how the program would work. So pseudocode. So start. Line 2. Answer, is speed slow enough to open parachute? So we're storing the result in answer. Line 3. If answer equals yes, open parachute. If answer equals no, do nothing. So we're checking the speed and deciding whether or not to open the parachute. Why would you get fired if you wrote that program? Well, yeah, that's what, yeah? Yeah, it'll do it once. So you'll start. So imagine this spacecraft that's say 1 mile, 2 miles high. It'll just execute this. It'll go start. Is it high enough? Are we going slow enough to open the parachute? No. Do nothing. Stop. So it's checked it. It's decided it couldn't open the parachute, and then it just gives up. So so the result will be when it gets close to the ground, the parachute still won't be open because it's just run the program and it's finished, and it won't bother opening it. So this is a bad program, and the result would be this. So I think this is actually a result of a parachute not opening. I think this was the Genesis spacecraft. I'm not totally sure what happened in this disaster, but it doesn't look very good, does it? Especially at that price. So what we want is something called a loop. And loops in computing are basically a way of repeating something again and again and again. So this is a better program that you would not get fired for writing. So here we go, line 1, start. Line 2, answer, is speed slow enough to open parachute? Line 3, if answer equals yes, open parachute. Line 4, if the answer equals no, do nothing. Now this is the key bit. Line 5, go back to line 2. So it then goes blop, and then we run it again. Is speed slow enough to open parachute? Is the answer equals yes? Is the answer equals no? Line 5, go back to line 2. Plop. So how long will this program run for? Forever, yeah? Perfect. So and the result is your parachute opens and your astronauts are saved. Okay, fantastic. Now, a bit close to home, here's another example of a loop that you'll have in your car. So there's a paranoid computer in your car continually checking if you crashed it all the time. It's saying, have I crashed? Have I crashed? Have I crashed? And if it crashes, it'll open the airbag. So let's go through this line by line. Answer, has the car hit an object? If the answer equals yes, open the airbag. If the answer equals no, do nothing. Go back to line 1. There we go. Answer, has it hit an object? And it repeats round and round and round and round again. So always, there's a piece of software in your car just waiting to open that airbag for you. And it's always a computer that's probably doing it. So this is an example of a loop in engineering. It's just a way to get code to repeat again and again and again. So now we're going to move on to MATLAB, and I'm going to teach you about for and while loops. And there's two distinct types of loops that are pretty useful in different circumstances. So in MATLAB, if I wanted you to write a program that printed the word hello, 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 and make a super friendly computer that repeated the word hello 100 times, until now, what you'd have done is you'd have just typed this in again and again and again, or if you're clever, you'd have used copy and paste, and you just generated a linear program, and it would print out hello again and again and again. But let's make our first loop in MATLAB, and let's turn this linear program into a program with a loop. And this is your first loop in MATLAB. And so it's your first for loop in MATLAB, okay? So for loops is a special name for a special type of loop. For loops always start with the word for, and they always end with the word end. And everything between for and end will be repeated, okay? So we start here, it executes display hello, end, goes to top, for execute display hello, go to the end. So it goes round and round and round there, and the result will be we print out hello a certain amount of times. Now, what's missing from this code? Sorry? I had the right answer there somewhere. Yeah? Yeah, exactly. So what we're missing here is the number of times it repeats. Very good. Thank you. Please shout out. I like people that shout out. So what we need to do is tell MATLAB how many times we want to repeat this. Now, what we do, so you notice, if you just look at this space here, I've just put in n equals 1 to 100. And what this means in English is count using the variable n from 1 to 100. So this means literally count using the variable n from 1 to 100. So there's n, there's the start value, and there's the end value. So let's have a look at this in a little bit more detail. So what I've done is I've broken this for loop down into like a flow diagram that we'd have had in the first lecture. So you remember that these flow diagrams are the triangles and the squares. And let's start off. So it starts off and it goes for n equals 1. So this means set n equal to 1. Then it executes what is ever between for and end. So in this case, disp hello. So it executes disp hello. Now you can't see this step at all in this for loop, but then it goes n equals n plus 1. So automatically the for loop will add 1 to n. So what's n now? Huh? What's that? Go on. 2. Okay. So is 2 smaller than 100? Yes. Go round. Okay. Disp hello. N equals n plus 1. What's n? 3. Is 3 smaller than 100? Yes. Go round. Disp hello. N equals n plus 1. What's n now? 4. Is it 4 smaller than 100? Yes. Go round. It will keep going round here, adding 1 to n, until it gets to that final value there that is 100. So what we're going to do now is look at a video example of this, because I know just going through stuff on the board is quite theoretical. So I'm going to show you it in action. Whoops. Right, here we go. So disp hello, I think. Now I'm going to copy and paste this a few times. And run it. Boom. Hello 4 times. Now we're going to turn this into a for loop. For n equals 1 to 4 end. Same thing. Okay, so we've just made our first for loop. Now we can change this number to as many times as we want. So 100. 100 times it's printed out. Lots of times. Let's run it. Now what I'm going to do now, because I don't want to wait a million times, is I'm going to press Control-C, and this will terminate the program. Control-C stops programs on most computers. And I guarantee you, very soon you'll write a loop that wants to run forever, and the only way you can stop it, apart from rebooting the computer, is Control-C. So, that's that. Whoops. Are there any questions so far? Are there any burning questions I can answer? You're all happy? Yeah? Okay, right, let's move on. So we did that. Yes. So this variable n, so I showed you that every time we go around this loop, we're adding 1 to n. But actually, at the moment in this program, we're only using n to basically decide how many times we repeat the code. But you can actually access this variable n within this loop. So for example, if you suddenly wanted to write a program that printed out hello 1, hello 2, hello 3, hello 4, hello 5, hello 6, hello 7, you could do this very simply like this. So you'd write this for loop. So for n equals 1 to 40, that means count from 1 to 40, disp hello, and then you can access n within the loop. So you can go print n, or disp n, end, and it will go round 40 times, so around there, around there, around there. And every time it will print out and tell you what iteration it's on, so it'll print out the n. And this can be very useful because you can use this to do all types of things like summing up numbers, integration, things like that we'll move on to in a minute. Yes. And the final thing I want to tell you about for loops is there's no need to start them at 1. You can start them at any number you want. So imagine you wanted to count from 50 to 100. You could start this loop off at 50. So what I've done is I'll replace this 1 here with a 50. So this will go n equals 50, n equals 51, n equals 52, 53, 54, 55, all the way to 100. And here's the output of that program. So it would be hello 50, hello 51, 52. Am I labouring this point too much? Is this blatantly obvious? Or would you... It's pretty obvious, is it? Am I going too slow? Okay, well, I want to make sure everybody's got it. Okay. Right. Now, let's look at our very first example of using a for loop to do something useful. So imagine I said to you, add up the numbers from 1 to 200. So you could do it with this program here. Or if you didn't want to do it with a for loop, you could do it like this. You'd go sum equals 0, n equals 100, sum equals sum plus n equals 101, sum equals sum plus n equals 102, sum equals sum plus n, 103. So there's a very repetitive way of finding out the sum of the numbers from 100 to 200. But now we can do for loops. We can add up all these numbers in a few lines of code. And the code looks like this. So I know this is a bit tedious at the moment, but it's going to get very, very powerful very, very quickly. I've got to cover the basics first. So firstly, we initialize our summing variable. So at this point, we say sum equals 0. And we go, let's count from n equals 100 to 200. So we counted from 100 to 200 with the variable n. Then in this loop, we go sum equals sum plus n. So what it'll do is it'll go sum equals 0. Then we'll start off n equals 100. And it'll go sum equals sum plus 100. So sum is now 100. We go round. So n is now 101. Then we add 101 to sum, and now that's 201. And then we go round again, and n is 103. We add 103 to sum, which is whatever the last number was, and we go round, 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 and we basically adding up all numbers from 1 to 100. Is that clear? Yeah, I'm seeing nods. Anybody find that not clear and want me to explain the detail? Stick your hand up now. I'm very happy to go over anything again. Okay, good. So now we can do loops. We can do for loops. Yeah, so here's this flow diagram of this whole process. So I don't think I'll go through this. Well, I will. I'll go through it very quickly. We set sum as 0. We set n equals 100. That's the first number. Sum equals sum plus n. Then the for loop automatically adds 1 to n there, checks if n is smaller than 200, go back to the top, and repeats adding 1 to n until n is not smaller than 200, and then we finish the loop. Okay? Now, I would like you now to turn your lecture notes over. So Good, so do turn them over. Now, don't cheat for this example. So I'd like you to have a go at doing this now. So please don't look. I've actually printed the answer because I find it personally irritating when lecturers don't print the answers in the lecture notes. So just don't cheat. And there's no prizes, so there's no point in cheating, okay? So I've made this linear program, okay? And this program starts off with s equals 9.5 and x equals 1. And then we apply this formula, we apply this formula, and we apply the same formula 50 times. So what I'd like you to do is turn this into a program that uses a for loop, okay? I'm going to write on the board, so you don't have to cheat and look in your notes, what a for loop looks like, just to remind you again. So, for, and I'll do this from 1 to 10, just so you've got to change the numbers. So just have a go at writing that out. And if you finish early, have a go with a calculator and try and figure out actually what this program's doing, what the point of it is. It's not actually a pointless random program. I'll just wander around. I'll give you like 3 minutes. I'll wander around, have a little look at how you're doing. Yeah, looking good. How you doing? You haven't turned over, have you? Doom. How you doing? That's looking good, yeah? Yeah, that looks good. You got to turn it over, otherwise there's no fun. Yeah. If it's a
so when you set sum equals 0.
Yeah.
So 0 plus 100.
Yeah.
Then the sum will increase to 1.
It increases to
So
100 because it's 0 plus 0 plus 100.
Are you then doing 100 plus 100?
Yeah, then it's 100 plus 101, 100 plus 102. Yeah, exactly. No, so it goes. I can't give you. I don't have time at the moment, but it's basically it goes 100, 101, 102, 103. You're always adding that to some. Does that make sense? We can chat about it afterwards. That's looking good. See the back row. I can look at the back row. Yeah? Oh, you finished. That's brilliant. Fantastic. If there were sweets, you would have had one. How are you doing here? Yeah? Looking good? Oh, you're on the calculator already. Good stuff. Any idea what it does yet? No? Okay. Looking good? How are we doing here? Yeah? Somebody's finished. Fantastic. How are we doing here? That needs to be up there, and you didn't end. Okay, what's that like? Yeah, okay. Any idea what it does yet? Guys, the calculators? Okay, so I think most people have done that. I just wanted to just have a little practice at doing that before we go into lab. Now, this is actually quite a cool program. What it actually does, so you can turn your notes over now. What it actually does, so that's the correct answer, is it calculates the square root of a number by successive approximation. So you know, like in maths, often they give you like an iterative series to evaluate, and they'll say like, solve this equation by putting the answer back in, and you put it back in, and you put it back in. This is what this is doing. So what it's actually doing is S is the number we'd like to calculate the square root of, and X is our guess. So what do you think the square root of 9 is? Or 9.5? What would you say it would be about? 3 something, okay? But I've given it a terrible guess of 1. And what happens is we pop 1 in this, and then the computer guesses, or its first guess at the answer is 5. And then we pop this back into this equation, and its next best guess is 3. We pop this back in, and the next best guess is 3.1. And after like 5 or so iterations, the answer's converged. And so now all those problems in maths where you have to put something back in and put something back in, you can just solve with a loop, and it'll do it for you in seconds. So I think you do that quite soon. Have you done that already yet in maths? No, I think you will soon. So that's a good engineering problem solver. Right, while loops. So now we've conquered for loops. We're going to move on to while loops. Now, while loops are very slightly more complicated than for loops, but they give you much, much more control over what's happening. I can't talk over you guys. So I've now taught you about loops, and you've gone back to your rocket ship, and you say, oh, I know about loops. I'm going to use use a loop and repeat my program again and again and again to check whether or not we should open the parachute. And you write this program for n equals 1, ... 10, end, and this is the solution. What's wrong with this now? What's wrong with this? Yeah? Yeah. Exactly. So what will happen is this will get to, I don't know, it'll be at 3 or 4 miles high in the sky. The computer will go, right, let's check if we should open the parachute. And it'll go, okay, n equals 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It'll probably take the computer about a millisecond to go through this thing each time. So within about a second or so, the computer's finished checking whether it should open the parachute because it's gone through this loop 10 times, and then it gives up. It goes, oh, I've checked it. Who cares anymore? So what will happen then is that the capsule will still continue to hurtle towards Earth, and the astronauts will still die. So this is also a bad answer. So we need a different type of loop that gives a little bit more control with an undeterminate length this will repeat. Yeah, so that's the result again. So what we need is a loop that looks like this. Now, I'll just read it to you. While spacecraft is in the air equals yes, then we do our checking. Is speed slow enough to open the parachute? If the answer equals yes, open parachute. If the answer equals no, do nothing. Go around. While spacecraft is in the air equals yes, answer is speed slow enough to open parachute, etc., etc. So this will repeat. This will continue repeating whilst the space capsule's in the air. So it'll only stop running the program when this condition here is no longer true. So a while loop repeats while something is true. Okay, so while a condition is met. When that condition is no longer met, it stops running. So these are very powerful for sort of... have you guys got a question? I see you discussing. Have you got a question? No, honestly, if you've got a question, just shout. Sorry, shout out, I can't hear. No, so it runs what? That's a really good question. So the question is, thank you. So the question is, I won't say what's wrong, I'll just say what's correct, and then that'll answer your question. So this whole loop runs while the spacecraft is in the air. So we only run this while this condition is true. Does that answer it? Yeah, so it runs whilst this condition is met. Okay, so these are quite a powerful type of loop. So let's have a look at some examples. So this is your first while loop in MATLAB. Now this while loop is doing exactly the same thing in this circumstance as the for loop that counts from 1 to 10. So what we do here is we go n equals 1, and we go while n is smaller than 10. Okay, so while n is smaller than 10. So this will only run when n is smaller than 10. Disp n, display n. Now this is the bit that you don't have in the for loop, or is like assumed. So you then got to go n equals n plus 1. You've actually got to type that in. You've got to say add 1 to n. Then we get to the end, and it goes back up to the top. While n is smaller than 10, so for the second time around, n will be 2. N is smaller than 2, so let's carry on. Disp n equals n plus 1, so now n is 3. Go to the top. And it just keeps going around until n gets to bigger than 10. And we just count from 1 to 10. Now, if you go back, so if we go back to that for loop, you see here, this n equals n plus 1, and this like comparison to 200 is almost sort of taken care of us, for us by the for loop. You don't actually need to write n equals n plus 1 anywhere, okay? But in the while loop, it does not take care of that. You've got to write it yourself. And what this means, you get a bit more control to like control program flow, but you've got to do a bit more work. So while loops are quite handy. Yeah, so here's the flow diagram. So n equals 0. Is n smaller than 10? Yes. Disp hello, n equals n plus 1, go to the top. Is n smaller than 10? Well, it's 2. Disp n equals n plus 1, go to the top. Is n smaller than 10? It's 3. And it goes all the way around here until we get to n is not smaller than 10. No, stop. Just prints out the numbers 10 times. Any questions on that? Any burning questions? Do shout out. Because if you're thinking it, somebody else probably is too. No? Right, onwards. Now, the really good thing about while loops is you don't have to count up in ones, like you do with for loops. You can count up in any increment. So you can count up in 0.1s, 0.5s. You know, you've got control because you're specifying this adding command. You've got control to specify how quickly you count up. So how are we doing for time? Oh, all right. So here, this program will count from 0 to 10 in steps of 0.5. So here we go, t equals 0. While t is smaller than 10, the time is disp t equals t plus 0.5. Go to the end, go to the top. T is smaller than 10, etc., etc. So t equals t plus 0.5. And the result would be this. Time is 0, time is 0.5, time is 1, time is 1.5, time is 2, and the end time is 10. So you're actually counting up in steps of 0.5. And this is very useful. Yeah, so far we've used, in while loops, this smaller than comparison. So we go while t is smaller than 10, while n is smaller than 10. So, by the way, this can be anything. You can call this variable here t or n or z or your name or my name or whatever you want. You've got totally free choice to define this variable. But there's lots of other conditions that the while loop can use. So we can execute the while loop. So we've used the less than command, so it'll run while y is smaller than 5. But we can also use the greater than command, so we can go while y is bigger than 5. We can also use the less than or equal to sign, so while y is smaller or equal to 5, greater or equal to, or not equal to. So you've got all these conditions that you can control when your while loop runs or when it doesn't run, just by replacing this little sign here with whatever you want. Now this is a trap. I'm going to show you this trap now. Everybody, always, in your code, forgets this. Notice here, this is two equal signs. When you want to do a comparison in MATLAB, you use two equal signs. You do not use one equal sign. Your program will not work if you put in one equal sign. And I promise you, you'll all make this mistake, and I make that mistake also today. So have a go at that, and we'll visit this later again. Right, we're actually doing quite well for time. So the next thing I want to talk to you about is nested loops. Now this is when we start mixing it up and making it much more powerful. And the examples I've done to date are sort of engineering, or not really engineering related. I've just had to teach you the basics, the fundamentals, before we can go on to interesting stuff. So I'm now going to talk to you, oh, my microphone's that's better. I'm now going to talk to you about like engineering examples. And they're called nested loops. I like this image of Russian dolls. Can you see they're nested, like going in one another? This is what effectively nested loops are. So here's an example of a nested loop. And this is where it starts to get very useful. In this external loop here, we're counting using x from 1 to 5. So this loop will go x equals 1, x equals 2, x equals 3, x equals 4, 5, etc. This, and between this 4 and this end, we've written yet another loop. We've written another loop. And this time we're counting with y. And we're also going from 1 to 5. So this will be y equals 1, y equals 2, y equals 3, y equals 4, y equals 5. Yeah, and that's it. So what will happen when you run this all together is it'll go x equals 1, y equals 1, 2, 3, 4, 5. Then it'll go up to the top. X equals 2, y equals 1, 2, 3, 4, 5, etc. Then x equals, or skip to 4. Or I'll skip to 5, x equals 5, y equals 1, 2, 3, 4, 5. And I've just used the Sprintf command to print out the x and the y that we're currently at. So where could you use this type of loop, this type of nested loop? Can you think of just a silly example? Anybody? What do you think? What's it remind you of? No? Maps, matrices, accessing data that's like on a grid. So what we're doing here is basically we're generating x and y coordinates at various points. So the result will be we have x equals 1, y equals 1, x equals 1, y equals 2, x equals 1, y equals 3, x equals 1, y equals 4. And we're basically just iterating over like coordinates in a map or coordinates of a matrix. Or, you know, so this is very useful for exploring 2D spaces that we'll look at in a moment. Yes, so. Yeah, so what this can be used for is basically iterating over matrices. So you see here, or 2D arrays. Here, we've defined an array, and it's got coordinates 1 to 5 and 1 to 5 there. And what this would enable us to do is basically access this point, 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 doing like scan. And that's very, very useful, as we'll come to see in a moment. So, very often in engineering, and I think you're probably doing this in maths now, you need to visualize a problem. And in this problem I've just made up, we've got the sea, and we've got a harbour. And we want to figure out what the height of the waves will be at the back of the harbour and find out if they're going to kill our pedestrians. And you've done some fluid mechanics, and you've solved some wave equations and things like that, and you've come up with this equation to describe the height of the waves in this harbour. And it's a function of x and y, so here's x along the harbour, and here's y. And it's also a function of t, and it looks horribly complicated, and it doesn't look like the type of thing that would be very nice to analyse by hand. So we've got, let's have a look, x of y is equal to sine x 0.8 plus t sine y 0.2 exp. So it's quite a nasty function. And what you could do is you could get out some graph paper, you could do some differentials, you could maybe evaluate this at various points and sort of, I don't know, draw it at various points and plot out the answers. And if you really put your mind to it, you could evaluate that on graph paper and you'd probably find the answer. But you probably won't be able to do that when it gets much more complicated. So we need some type of a slick way to evaluate this equation and figure out basically what the shape of the waves at the back of the harbour, or how high they are. So we're now going to do this with MATLAB. So we can do this with our nested loops. So this is where it gets useful. So firstly, you notice this equation that describes the waves in the harbour is a function of time. So let's just make our lives easy and say it's at time 0 to start with. We'll come back to that later, but let's just say at time 0. So here we go, t equals 0. Now, you might remember this command from, I think, 2 lectures ago. So zeros means make me a 2D array of zeros. So we're going to make a 2D array of 60 by 60. Let me just look. 5 minutes left. So we're going to make a 2D array of 60 by 60. And we're going to store it in H. So this initializes like a nice big square chunk of memory. We're then going to use this nested loop here to iterate over each one of these positions in this 2D array. So we're just going like, look at this position, look at this position, look at this position, look at this position, look at this one, now go back to here, look at this one, look at this one, look at this one, look at this, etc., etc. So here we've got a for loop counting with x from 1 to 60, and here we've got a for loop counting with y from 1 to 60. So what will happen, just go through it, is we'll go for x equals 1 to 60, so now x is 1, and we'll go for y equals 1 to 60, so y is 1, 2, 3, 4, 5, 6, etc. to 60. Go to the end, x will be set to 2. Now x is 2, y is 1, x is 2, y is 2, x is 2, y is 3, etc., etc. So we're evaluating this, we're basically counting over this grid of x and y. Now, in the middle of this nested loop, I've just stuck this equation. So I've literally just typed in this equation here. And notice I've said h equals x comma y, and then this equation. So what this will do is this will store the result of this equation here, evaluated for x, for y, and for t, which is 0, at each x and y position in this 2D array. So we're evaluating this equation at each point. And then the final command is this surf command, which plots the 3D array. And this is the result. So we can actually visualize the waves in the harbour, which looks pretty cool. So now you can evaluate 2D expressions like with them in 2D space and look at them and see what they look like, and maybe tweak your equation and see, manipulate the answer. So this is pretty handy for many areas of engineering. It's going to get much better. So we solved it at time t equals 0 initially, because I said, let's simplify the problem. Let's start off with a nice, easy... Was that somebody yawning? No? Okay. Almost done. Almost lab time. So we kicked off with evaluating this equation here at just t equals 0. So t equals 0. But, the solution changes a function of time. So if we evaluate this equation at t equals 0, the waves at the back of the harbour might be at a minimum, they might be a maximum, we don't know. So what we really need to do is evaluate this as a function of time. So what we're going to do is we're going to use a while loop to evaluate this whole equation as a function of time. So here we go, t equals 0, h equals 0, 60, 60. So this is making our 2D empty array. And then notice we've got third loop here. We've got a third loop. We go while t is smaller than 20, so this will run whilst t is smaller than 20. Then we've got this like double loop here that's counting over our x and y coordinates. So this is going x1, x2, x equals 1, then, so it's basically iterating over the 2D matrix. And then in the middle, then in the middle we're evaluating our equation at each point. So what will happen is t will be equal to 0. We'll evaluate our whole equation at every place in space for t equals 0. Then what happens, we'll plot it, and then we go t equals t plus 0.01. So we step forward in time just by 0.01. We then get to the end, we go back up to the top, we evaluate our whole equation again over the 2D space, we plot it, we step forward in time again by 0.02, and the process continues. So we're evaluating this 2D space at time steps incrementing about 1 millisecond. And by the way, you might be wondering what this pause command does. That's just to slow it down a bit, because the computer will evaluate this crazily quickly, and you won't be able to see what's happening. So I've just made it pause for a few seconds to slow it down a bit. And the result is this. So let's look at the video. Oh, are there any questions about that before I go to the video? Any burning questions? If there's something you don't understand, other people are probably thinking it. Okay, let's look at the video of this. Oops. Right, here's the program, and this is us running it. So what we can see is, firstly, I'm printing out t every time it's incrementing. So we can see as it's stepping through time here, t is increasing. So t is increasing, and we're plotting this graph again and again and again. So here we've got the one side of the harbour, and here we've got the back of the harbour. And we can actually look at the height of the waves here at the back of the harbour as the animation continues. Whoops. So here we go. Time's increasing, increasing, increasing. And, yeah, I'm actually counting to 800 just because it's in a lecture. I want to show you. I don't want to end abruptly at some small value. So let's maximize this, and we can really evaluate this equation in time, basically, now, and really understand what this equation is physically telling us. So you can now do this, and you've got the power to evaluate any equation that you're given by your maths lecturers in basically 2D space and in time. So that's pretty cool, I think. All with loops. So that's it. That's the end of the lecture. We're exactly on time. So off to the lab. Yeah, thanks very much.